Hello. We've been using a debugger to show us the values of registers, but let's try to make this program do it. So let's say that we have something in a register, a hexadecimal number, and to show it with a function like message box, we need to make a sequence of characters, one character for each digit. For start, let's make it a single character. So let's make a placeholder here and see what can we do to extract a single digit out of this number. We know that every hexadecimal digit is exactly 4 bits, 4 binary digits. Therefore, with an instruction like this one, we are going to zero all the upper bits of this number and leave only the 4 bits that corresponds to the lowest hexadecimal digit. Let's take a quick look in a debugger. So now we have this number in EAX, we execute the AND instruction, and only the lowest hexadecimal digit remains in the register. Therefore, we have extracted the value of a single hexadecimal digit. This is a number from 0 to 15. And to make it into a character, we can simply add code of the digit 0 to this number, and we should get a code of another digit. We can write the code directly, or we can just write it as character. And let's store this single byte into a location that is then passed to the message box function. It shows digit 8, so it appears to work. However, a hexadecimal number can also have some letters, and when we try it now, we are going to get some symbol. This is because in the ASCII coding, after digits we have several symbols, while for hexadecimal digits we would like to have after 9 A, B, C, D, E, and F. So we need to handle this gap. We can check whether this digit is higher than 9 or lower than 10, perhaps. Jump if below 10. We can make some label here. So if below 10 we jump to this instruction and we just add code of 0 character, and otherwise we need to adjust for this gap. So we can just add 7 to skip over this gap, or we can also write it as a difference between these 2 characters, or even like this. Okay, now we have the E letter displayed. We also have this function called that converts it to lowercase. We can skip it for now. And we can also do this with a table. just like we did here. So let's make a table of digits. You can simply write them down, and letters. And then here we can copy a character from the table with index in EAX, because we have entire EAX register prepared. So this selects a correct character for a digit. And now what can we do to get another digit out of this number? We can try shift instruction. This is a shift right. We are going to shift EAX register to the right by 4 bits. And this instruction is going to shift all the bits in this number. The 4 lowest bits are going to be shifted out of the register and disappear. And on the other end, we are going to get 4 new bits shifted in. They are all going to be zeros. You can test it in debugger, but first let's add another instruction to test. Shift left. So after we shift right, we are going to shift left by the same number of bits. We have this number in EAX. We shift right. So now the 4 lowest bits have been shifted out of register, and we have new 0 bits shifted in on this end. And when we reverse this with shift left by 4 bits, now we have new 4 zeros shifted in on this end. So the original 4 bits that were here are lost. But we also have another option. We can use rotation instructions. Rotate right and rotate left. And this time the bits that are shifted out of register here are going to arrive on the other end. So the E digit is now here. And when we shift left, we do the same in the other direction. So we have the original number restored. And for example, when we use this instruction, rotate left by 4 bits, then we are going to get this uppermost hexadecimal digit shifted in on this end and displayed by this code. So now we see the uppermost hexadecimal digit. And we can do this in loop to show all the digits of the number. So let's make a placeholder for 8 digits. And repeat it 8 times. We keep repeating until we have 0 in ECX register. So this is going to be repeated 8 times. We need this number in another register to not get destroyed here, because we do some other operation with EAX. So we are going to just move this value into EAX, convert into character, and then rotate the original number, and so on. Keep repeating this. And also we need to store the characters at consecutive positions in memory, so we need to move this pointer. We can use another register for this purpose. And increment the pointer each time. Let's try it. And now we have entire number displayed. So now we are able to show the content of register without a debugger. And in fact, let's put it into our function now. So this is now going to be a different function. Let's call it showHex. We no longer need this table. But the number in EDX we need to read from the parameter to the function. Oh well, we already have this. So here we store the parameter on the stack. And call the function. It works. And one more thing we can do is to not use a global buffer for this function, but allocate this space on the stack locally. So we need 8 digits plus 0 byte, so we need 9 bytes. But on the stack we want to allocate in multiplies of 4, so let's allocate 12 bytes. And this is local area. So here we have, at this address we have 12 bytes that we can use for any purpose safely without interfering with any other function of the program. So we need to move this into EDX and subtract 12. And then we are going to use this function to display the converted number. So again, we need to have this address. This time, for example, in ECX register. And it seems to be working. We can try with another number. And we can also simplify this a bit, because if we tried to access this memory directly, then we could use this addressing. And there is also an instruction that allows us to copy the computed address of such memory operand into a register. This is called load effective address. So this simply computes this address and stores this computed address into a register. So we can also use this here. And now that we have a function that can show us any value, we can do some experiments even without debugger. So for example, we have number 1. When we shift this value to the left by 1 bit, this is the same as multiplying this number by 2. And similarly, if we shift a number to the right 1 position, this is like dividing the number by 2. Even if the number is not a multiple of 2, we get a correct result and it is simply rounded down. And what about negative numbers? For example, -1 when we shift to the left. This is in fact correct encoding for -2. But if we try in the other direction to shift -2 right 1 bit, then we do not get a -1 because the uppermost bit is cleared. And of course it is cleared because shift right shifts new bits that are zeroed on the top end. And for this reason we have another instruction called shift arithmetic right, which works for signed numbers. And the difference is that the new bits that it shifts in on the upper end of register are the same as the signed bit was. So in this case we get -1. So when we use shift arithmetic, then this also works for negative numbers and can divide them by 2. And one more thing, it is possible to shift the value by the number of bits given in a CL register, but this cannot be any other register, it must be CL. Like here. So we can also attempt to construct this loop a bit differently. Instead of rotating the number, we can here be selecting the digit before the end instruction by shifting it to the lowest position, and we are going to track this position in CL register, which is the lowest part of ECX. So we can start from the 28 because to get the uppermost hexadecimal digit we need to shift it right by 28 bits. And then every time we are going to subtract 4 from this. So next digit is going to be shifted 24 positions to the right, and so on. And we are going to continue until we go into negative range. So when this is 0, it is still okay. We are going to shift it right by 0, so leave it unchanged and select the lowest digit. And after we have 0 in ECX and we subtract something, then we are going to have carry and we terminate the loop. So let's take a number to test it and see how it works. It seems to work correctly. So this is another way of doing exactly the same thing. Thank you for watching.